Hey guys, and welcome to Scientific Drinking. Tonight we're going to be talking about a topic that you might find a little dense: black holes. Cheers. So what exactly are black holes? I mean, they're holes in space? Not quite. A lot of pop culture references depict them as a lot of things. So are they deep space vacuum cleaners? No. Are they just wormholes? Nope, not those either. Are they portals to the fifth dimension? Probably not. Are they extremely dense objects that distort space and time and from which there is no escape? Probably. But we don't know for sure because we can't actually see black holes, but we'll get back to that in a minute. Black holes are depicted in a lot of these ways in pop culture. So popular movie examples might be The Black Hole from Disney, or Event Horizon, which depicted space as sucking the spaceship in, and even at full thrust it couldn't quite escape. Or even the most recent example was perhaps in Interstellar, which showed it pretty close to what it was as a distortion of space and time, until it got to the end and there was that fifth dimension weird book thing, which probably almost certainly isn't what happens with black holes, but we don't know for sure, admittedly. In video games, you might have seen other examples, like in No Man's Sky, which pretty much just uses black holes as wormhole proxies. Kind of ridiculous, but admittedly, that's not the only problem in No Man's Sky, so we won't overanalyze that. Everspace depicts black holes as kind of space vacuum cleaners from which there is no escape. Popular mantra, but definitely not the case. Probably the most accurate depiction I've seen in video games is Elite Dangerous. Now, after they got rid of the thing where you can fly through the center of black holes in one of the earlier patches and made them actually have a gravity gradient, they became pretty interesting and pretty real. So I'm always worried that I'm gonna drop out of hyperspace right into a black hole and I can't see it, right? Because you can't see black holes unless something's falling into them. You can see on how they interact with things around them. But the one thing that they couldn't really do in the video game is depict the time dilation that occurs around the black hole. Now we'll talk about that in a minute. So what happens if you fall into a black hole? I'm sure a lot of people have wondered that, and perhaps me more than the average person. It has consumed a tremendous amount of my time. I don't specialize in black holes, I specialize in rockets, but black holes are still very fascinating objects, so I can't answer the question of what happens when you fall into a black hole, but it depends on how big the black hole is. So that fellow behind me is Herb. Herb's falling into a 9-centimeter black hole. That's right, 9 centimeters. And that's gonna become important in a minute. What's gonna happen to Herb when he falls into this tiny little infinitesimal black hole? Can that really hurt him? Can it do anything? Does it have even gravity? Well, yes, and yes. Falling into smaller black holes is actually more terrifying than falling into big black holes like Sagittarius A star, which is the black hole at the center of our galaxy. And the reason why they're more terrifying is because of something called a gravity gradient. Gravity gradient is the difference in gravity at your feet relative to your head. Now, on Earth, that's pretty much nothing. There is a difference, but it's very, very small. Now, this difference is also kind of a problem when you're talking about spinning spacecraft. If you make the radius of the spinning spacecraft too small, when you're trying to stand on the side to create artificial gravity, you're going to notice a difference in gravity between your head and your feet. Well, with black holes, small black holes, it's kind of a similar thing. The smaller the black hole is, the greater the change in gravity relative to the size of the surface. So let's depict a gravity gradient for Herb to experience. So this spiderweb looking thing behind me is a gravity gradient, or at least my depiction of a gravity gradient. Notice the lines get denser and denser the closer you get to our 9-centimeter black hole. While Herb is far enough away, he doesn't experience much effect from this gravity gradient. But let's move Herb closer. So now Herb is experiencing this gravity gradient. At first, it's gonna start pulling and stretching him. It's kind of like a medieval torture device. Stretching and pulling him thinner and thinner. And eventually he's gonna snap in half. But that's kind of bloody and gruesome. So let's draw it. So this is Herb. Was Herb. He's been snapped into 3 pieces with his head, his intestines, his legs, and his body all stretched out and sprawl out across this black hole surface. But Herb isn't done suffering yet, because the closer he gets to that black hole, the more he's gonna stretch and pull in a process we call spaghettification, until he is nothing more than a single line of molecules thick. But what happens if Herb falls into a really big black hole? And I'm talking really big. So this is Herb falling into Sagittarius A star. Obviously, this isn't quite to scale, but let's assume that this is kind of a somewhat realistic depiction of Sagittarius A star and Herb falling into it. Is he going to be stretched and spaghettified? No. Like I said, the smaller the black hole is, the greater the gravity gradient, the difference between the gravity at your feet and your head. But with Herb here falling into Sagittarius A star, which mind you is about greater than the radius of our entire solar system, it's absolutely huge. He's not going to feel anything when he passes beyond the event horizon, at least not in the terms of gravity gradient. What Herb will experience is a slowing of time, or a speeding up of time, depending on your perspective. Herb's falling into this black hole. He has a different frame of reference than someone who's watching. Now remember we took from our last video when we looked at different frames of reference for the NRHO, the near rectilinear halo orbit in which the gateway is going to be placed. We saw the frame from the Earth inertial frame, the Moon inertial frame, and the Earth-Moon rotating frame. Those are all different frames of reference. Similarly, Herb and a spaceship orbiting the black hole are going to have different frames of reference. And because the gravity of the black hole is so great, that's going to be a very different perspective. So for Herb, as he falls into this black hole, he's going to see all of the universe seem to speed up. First, that spaceship that's hovering and watching him is going to orbit faster and faster, and then it's probably going to be gone because it can't orbit forever. From the spaceship's perspective, Herb is going to slowly get more and more red, and then he's going to disappear because the wavelengths, the light that he is reflecting or emitting, is getting longer and longer as he is slowing down relative to the observer orbiting the black hole. Now I know that's a little bit weird to think about. Anything dealing with black holes is weird to think about. They are the most extreme things in our universe. But how will Herb die? It's always an interesting question, right? How are we all going to die? But Herb has an especially interesting death. Falling into this supermassive black hole at the center of our galaxy is actually going to see everything speed up, right? So all of those light sources, those stars, everything that emits light in the galaxy is going to get brighter and brighter because he's seeing their entire life play out before him. All the photons that are going to fall into the black hole and would hit something that's moving slower than the speed of light are going to hit him faster and faster. Soon he's going to be blasted with so much radiation that he's just going to cook. Now that's assuming his spaceship has enough air and water and food to let him survive that long. But for Herb, let's assume he has a special spacesuit that first of all lets him have all the food, water, and air he needs. And then let's take it a step further and say that all this radiation, it's not going to hurt him. So if he's not destroyed by the radiation and he has all the air and everything he needs, he's going to see the entire lifetime of the universe play out before his eyes. Recent evidence suggests that the Hubble constants may not be what we thought they are, and an even more recent paper suggests that the universe might be a sphere. And that's really sci-fi, isn't it? Kind of weird to think about. All right, so I told you before that 9 centimeter black hole is going to become important. A 9 centimeter black hole like this one here, to scale. Pretty small, huh? How much damage could that really do? Well, it's hard to imagine. We already know that'll mess up Herb pretty bad. But could it swallow a spaceship, a planet? Well, 9 centimeter black hole is an important metric because the mass of that 9 centimeter black hole is 10 times the mass of the Earth, crushed into something that big. At least that's the radius of the event horizon, the Schwarzschild radius, the point at which no light can escape. Now, what else is 10 times the mass of the Earth? Well, if you keep up with scientific publications, the mysterious, enigmatic, and theoretical Planet 9. Planet 9 is supposed to be an object orbiting the sun much, much further out than the Earth orbits the sun. That kind of passes around the outer reach of the solar system. Now it's theorized this way because when you look at the orbits of some of these trans-Neptunian objects, they seem to be in resonance with something that fits this description. So if you take something like that and crush it into a black hole, this is how big it's going to be. Now I'm talking about this because this is the result of a recent publication that hypothesized that this hypothetical Planet 9 could in fact be a primordial black hole. So in order to form a black hole, usually you need about 10 solar masses in order to have enough mass and gravity to pull that matter into a black hole. But there are exceptions to this rule, and one of those exceptions is something called a primordial black hole, which I've got behind me. And that was left over from the Big Bang. If it was one of these primordial black holes, it's been around for about 13.8 billion years, as far as we know. Does something with 10 solar masses have enough mass to last that long? Now, we know that there is something called Hawking radiation, and Stephen Hawking postulated this during his thesis presentation, which was given by his mentor on his behalf, because at this time he was already constrained to a wheelchair. The formula he presented was this one over here, the temperature of a black hole, which is unusual by itself because Gm is in the denominator of the equation, which is very unusual. Most of the time, that's the gravitational constant times the mass of the object is always in the top, the numerator of the equation. Second, h bar c, the Planck constant, and the speed of light is in the numerator. Again, a little bit unusual. But this pretty much says that black holes radiate, which is something we really never thought about before. It was impossible. They were dark stars. Nothing can escape something that has an escape velocity of the speed of light. Not necessarily true. The way black holes emit radiation is at the poles, polar vortices, at the surface of the black hole, where virtual particles, which are particles that pop in and out of existence and constantly annihilate each other over and over again. So matter and antimatter just pop up and annihilate each other, theoretically at least. So if one of these virtual particles forms at the edge of a black hole, you'll have one piece of matter, one piece of antimatter, and one will get sucked in the black hole and the other one will escape. But why am I talking about Hawking radiation? Well, funny enough, the smaller a black hole is, the hotter it is, the more radiation it has. So this is one reason why these black holes theoretically created at CERN, they slam particles together. Even if that did create a black hole, the temperature would be so extreme that it would immediately evaporate and wouldn't have a chance to form anything that would, say, suck the Earth in. Remember, they're not deep space vacuum cleaners. So what about a 9-centimeter black hole? If it's emitting radiation, how hot is it and how long does it last? Well, if we plug everything into that equation and use that bottom equation down there, which is the evaporation time of a black hole, then we come up to the time 2.98 times 10 to the 60th seconds. 2.98 times 10 to the 60 seconds. That's a long time. That's definitely longer than the age of our universe. So I guess it could be around. Mathematically, it works. Why couldn't Planet 9 be a black hole? Wouldn't change anything, would it? If it's been there pretty much since the start of the universe. Been there long enough for objects to form resonances with its orbit. It hasn't really harmed anything else, right? The Earth has been around for 4 billion years, so if it was a black hole, it hasn't harmed us. Probably won't do it anytime soon. It's pretty far out there. Now, the last thing I want to talk about is the spin of the black hole. Black holes are supposedly perfect spheres, or at least that's one hypothesis. But the angular momentum must be conserved. Imagine a figure skater on the ice spinning with their arms out. If he or she pulls their arms in, they'll spin faster, right? Well, the same thing happens with a collapsing star. When the star collapses into a black hole, all of that spin energy must be conserved. And when it goes from something the size of the sun to something only a few kilometers in radius, then it's going to spin really fast. Speed of light fast. That's what happens with pulsars. Now pulsars, which are neutron stars, are spinning right about the speed of light when they first form and slow down over time. Black holes are right at that limit of the speed of light, which kind of brings into question about what's in the center of a black hole. If angular momentum must be conserved, talking about fundamental laws of physics here, there has to be something in the center of a black hole that's still spinning that's not quite a singularity. At least that's what physics kind of tells us. If you're talking about time dilation, what exactly does that mean? Well, that's a little bit above my pay grade. And if I do say so, pretty weird to think about. But there is one kind of caveat that happens with black hole spin. So the area around a black hole has the centripetal force from the spinning, but it's still within the event horizon of a black hole, and this zone is where a lot of weird things can happen. You can escape a black hole even though you're kind of within the event horizon, and this is called the ergosphere, and it's pretty weird to think about. And that concludes my video on black holes, and besides, I'm out of beer. Thanks for watching, talk to you later.